Hi, this is Moser with a quick tutorial on showing molecules, as well as a few other weird covalently bound things, using Lewis structures. After you've watched this video, you should be able to represent octet-conforming molecules using a Lewis structure. You should be able to identify a polyatomic ion as a group of covalently bound atoms which have collectively lost or gained electrons, becoming charged, and you should also be able to represent those polyatomic ions with a Lewis structure. What you already need to know is how to determine how many valence electrons an atom has, how to draw an electron dot diagram, as well as what a full octet is. So let's go ahead and get started. You will definitely need to pick up the Mr. Gooch tutorial on how to draw Lewis structures. It makes life much, much easier, and having a periodic table is also pretty handy. So take a moment and grab those, and then let's get started. We'll go ahead and start with this molecule, CBr4, also known as carbon tetrabromide, though we haven't gotten to naming yet. If you look at step 1 on your tutorial for drawing Lewis diagrams, the surefire Gooch method, the first thing you're going to do is figure out how many valence electrons this compound has. I like to make myself a neat little table like this, so I'm going to list the individual atoms as well as a row for total. And I'm going to jot down how many of each atom I have. You won't do all these steps forever, but when you're starting out, it's handy to just put your ducks in a row. So I know I have 1 carbon and 4 bromine. Well, if we want to look at the valence electrons that each has, we know that carbons each have 4 valence electrons, and there's only 1 of them. Bromine has 7, and there are 4 bromines, so that gives us 28 valence electrons. We have a total of 32 valence electrons in this compound. Great! That's how many valence electrons they have. Now, how many do they want? Well, that's the octet electrons. And carbon would like to have 8, so would bromine. So 8 times 1 gives us 8, 8 times 4 gives us 32. We've got a total of 40 electrons wanted between all 5 atoms. Okay, so how many are they going to have to share? Well, if we take the number that they want and subtract from it the number that they have, that's octet minus valence, what that gives us is the number that they're going to have to share. For this compound, 40 minus 32 equals 8 shared electrons. Now, because we know that a bond between 2 atoms is sharing a pair of electrons, the number of shared electrons divided by 2 will tell us the number of bonds that are present in a compound. In this case, we're looking for something that's going to give us 4 bonds. Okay, well, let's actually see what that looks like. One thing you should know when you're creating Lewis structures, if carbon's present, it's pretty much always in the middle, and here carbon is present, so we'll put carbon in the center, and we're going to surround it with those 4 bromines. We'll write in our bonds, and I'll go ahead and do those in a different color. 1, 2, 3, 4. That little line represents a bond. It represents a shared pair of electrons. Now there's one more thing that we're still missing, and that's the number of unshared electrons. Because a Lewis structure shows both the electrons that are being shared in the compound, as well as the unshared electrons that are on any of the atoms. That's going to become important when we start to talk more about molecular geometry. So how do we figure out how many they're not sharing? Great question. Well, if we take the number of electrons that they have and subtract from that the number that they're going to have to share, in this case 32 minus 8, what we're left with is the number of electrons that aren't being shared. In this case, 24 electrons. So how are those distributed? Well, this is when it's really helpful to think about what each of these atoms looked like before they bonded to anything. Remember your electron dot notation? Let's quickly draw the electron dot notation for carbon and bromine. So we recall that carbon had 4 valence electrons, and sure enough, it's now sharing on all of those 4 sides. Bromine, however, already had 6 pairs that we said it wasn't going to share with anyone else. Well, guess what? None of those have gone anyplace. Let's count up those unshared electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Hey, guess what? 24. That's a completed Lewis structure for carbon tetrabromide. Now, when we've completed any Lewis structure, it's really useful to just do a little double check. Number one, make sure that the number of valence electrons that you're showing in your structure is the same as the number of valence electrons that you figured out at the beginning. So we've just counted those 24 unshareds. Now, 26, 28, 30, 32. Great, because remember, each of these lines represents a pair of electrons that's being shared. So we are satisfied that we've shown all the valence electrons needed. Now, since both carbon and bromine are octet-desiring atoms, let's check to make sure that every single atom in this structure is satisfied. Well, let's look at our central carbon. 2, 4, 6, 8. Yep, carbon's happy. Let's look at the bromine. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Yes, all of our bromines are happy. So we've met the valence electrons that we knew we needed to. Our Gooch math, as I call it, lines up in that we expect these to be sharing 8 electrons, and we're showing 4 bonds. We're showing 24 unshared electrons, and everybody's happy from an octet perspective. Woohoo! Great. Now, this is a neutral atom, so the number of total electrons and total protons is even. We'll talk a little bit more about things that aren't later. Let's do one more nice neutral octet conforming molecule together. So let's try good old H2O, water, everybody's friend. Well, remember, first we want to jot down how many of each atom we've got, and here we have 2 hydrogens, 1 oxygen. This one's a little tricky because hydrogen is not totally octet conforming, but the Gooch math still works if you remember that hydrogen, well, we'll get there. First of all, let's look at how many valence electrons everything has. Hydrogen comes in with 1, and there are 2 hydrogen atoms, so it contributes 2 valence electrons. Oxygen has 6 and only 1 atom, so that gives us 6 valence electrons. We have a total of 8 valence electrons available. Now, this is where it gets a little weird. Hydrogen is not conforming, but as long as we remember that hydrogen is satisfied with 2, this is not a difficult molecule to draw. So, hydrogen satisfied with 2, there are 2 hydrogens. That means it wants 4 electrons. Oxygen would like 8, and there's 1 of it. So we get a total of 12, I'll put this in air quotes, octet electrons, even though hydrogen's not really getting an octet. So now we have to figure out how many electrons they're going to have to share. The number wanted, the octet number, minus the number that they actually have, the valence number, will give us this. And for this compound, 12 minus 8 tells us that they're sharing 4 electrons. Now, the number of electrons shared divided by 2 will tell us how many bonds we should expect to see. We're looking for a compound with 2 bonds. Okay, easy peasy. Let's try it. Well, there's oxygen in the middle with a hydrogen on either side. Why did I put oxygen in the middle? Well, remember in the last instance we said that if carbon's present, it's always in the middle. But it's carbon or the least electronegative thing. However, since hydrogen can only form 1 bond, we know that oxygen's going to be in the middle. The other easy way to look at these is if you have 2 of something and 1 of something else, the singleton's always in the middle. Okay, so we show oxygen with a hydrogen bound to either end, but we've been looking at hydrogen a lot and oxygen together, and it's always shown in this little Mickey Mouse formation, isn't it? Well, what haven't we done here yet? We haven't talked about unshared electrons. So if we subtract the number that they have and subtract from that the number that they're going to share, we see that there are 4 unshared electrons. Well, let's remember how they came into this. Oxygen, if you recall, did have 2 pairs that we said wouldn't be shared with anyone else. Well, the fact is those pairs haven't gone anywhere. They're still present, so we have 4 unshared electrons, and they're on oxygen. How do we know they're on oxygen? Well, there are a couple of things. Number one, hydrogen really only has space to have 2 electrons. It can't accept any more than 2. And where it's bonding, it feels like it's got 2. So hydrogen certainly can't have any unshared electrons. Hydrogen never has any unshared electrons. Oxygen, as I said, came in with these, and there's no reason to think that they went anywhere. Now, let's do our quick double checks. Do we have the correct number of valence electrons? 2, 4, 6, 8 valence electrons are shown. Yep, that's what we projected. Do we have the correct number of unshared pairs? 2, 4. Yep, that's good. Is everyone satisfied from an octet or not quite octet perspective? Well, let's check on oxygen first. 2, 4, 6, 8. Oxygen satisfied. Since hydrogen only wanted 2, the hydrogen, 1, 2, 1, 2, is satisfied as well. So what we have here is a completed Lewis structure for water, H2O. Now, as we get into molecular geometry, you'll learn that water is actually a bent molecule. So it's more correct to show it like that, but you haven't gotten there yet. Suffice to say, if you can get as far as showing this, it's a good start. You're going to soon enough understand why it's actually bent. Okay, now let's talk briefly about polyatomic ions. So a polyatomic ion is a group of atoms that are bonded to one another covalently, but then have lost or gained electrons and are now charged as a group. There are a number of these, and they become very important when we're talking about reaction chemistry later on. There are things like sulfate and nitrate, phosphate and hydroxide ions. Well, we're going to keep it simple for now, and we can represent these with a Lewis dot diagram. Let's start off with a very simple case, the ammonium ion. So the ammonium ion is a nitrogen atom that's bound to 4 hydrogen atoms, and the overall ion has a positive 1 charge. So in a lot of ways, doing the Gooch math to back up a Lewis structure for a polyatomic ion looks the same as it did for a regular neutral molecular compound. There's just one important difference. So when I'm getting ready to do the math for ammonium, NH41+, I'm still going to list the number and types of atoms, but I'm going to add this to my little table, gained or lost electrons. Now, because this has a 1+ charge, we know it's actually lost an electron. I know, it takes some getting used to. So I'm going to put this in, 1 nitrogen, 4 hydrogen, and -1 electron. When I figure out my valence electrons, therefore, I show 5 times 1, 1 times 4, and then -1. So instead of 9 valence electrons, I actually only have 8. When I calculate octet, nothing changes. I know that nitrogen would like 8, hydrogen is satisfied with 2, so the total number of octet electrons needed is 16. None of my next steps change. The octet minus the valence will give me the number of electrons that will be shared, and for this particular ion, that's 8 shared electrons. Number of shared electrons divided by 2 will give me the number of bonds, and that means I'm looking for 4 bonds. Okay. I'm actually going to take the step right now of drawing the old electron dot notation or Lewis dot structures for each of these, because it makes it really easy to see how nitrogen would bond to 3 of those hydrogens. Boy, they would just plug right in. Well, if you think about it a little further, it also makes it easy to see that in order to bond with a 4th hydrogen, nitrogen would have to lose that 1 electron. So let's go ahead and draw nitrogen bonded to 4 hydrogens with 4 bonds. There we have nitrogen bonded to 4 hydrogens with exactly 4 bonds. Let's do all our little checks. How many valence electrons are we showing? 2, 4, 6, 8. Hey, that's what we said we needed. How many bonds are we showing? 1, 2, 3, 4. Hey, that's what we said we needed. Now, what about unshared electrons? Well, remember, the number that they have to share is 8, and they only have 8 valence electrons. There are no unshared electrons. And that makes sense, because hydrogen can't have any unshared electrons, and nitrogen's kind of got its hands full. Let's check octet for everyone. Nitrogen gets 2, 4, 6, 8. Yep, it's satisfied. Each hydrogen feels like it's got 2, yep, 2, yep, 2, yep, 2. It's satisfied. The last thing you need to know is that whenever you're showing an ion in a Lewis structure, you have to enclose the overall structure in brackets and put the charge outside the bracket. That's it. That's a very simple polyatomic ion shown with a Lewis structure. We'll do more complicated examples later, but this should get you started. Get going.